Good evening, sir. My name is Vaina Kumari, Department of Civil Engineering. Today we will discuss about a part of mm, strength of materials, that is buckling of columns. Buckling of columns. Now we will introduction of buckling of columns. Buckling is a failure mode characterized by sudden lateral deflection of a structural member under axial load. It primarily occurs in slender columns subject to compressive forces. Understanding buckling is essential, safe and economical structure design. Types of buckling. There are two main types: elastic buckling and inelastic buckling. Elastic buckling occurs when the material remains within its elastic limit during deformation. Inelastic buckling involves permanent deformation and typically occurs at higher load. Critical load and onset. The critical load is the maximum axial load of a column can sustain before buckling occurs. It depends on the column material properties, geometry and boundary conditions. The calculation of critical load helps in designing columns, prevent buckling failure. Now we will discuss about Euler's buckling theory. Euler's formula provides a way to estimate the critical load for long slender columns. The formula states that the critical load is proportional to the elastic modulus of the moment of inertia. Euler's theory assumes ideal conditions such as perfect geometric boundary supports. Effective. Next, we will discuss about effective length and boundary conditions. Effective length and boundary conditions. The effective length of a column varies based on its boundary conditions, affecting buckling behavior. Fixed, pinned, free and partial restrained supports influence the effective length differential. Correctly assessing the boundary conditions is crucial for accurate buckling load calculations. Next, the slenderness ratio of column stability. The slenderness ratio is the ratio of column length of its radius of gradation. The higher slenderness ratio indicates the perforator susceptibility to buckling. Design codes often specify limits on slenderness ratio to ensure stability. Design considerations and safety factors. Engineers incorporate safety factors to account for uncertainties in buckling analysis. Material imperfections and load eccentricities can reduce the actual buckling capacity. Proper material selection, cross-section shape and support condition enhance the build. Post-buckling behavior. After initial buckling, same columns can carry additional load if deformations are managed. Post-buckling capacity. Post-buckling capacity depends on material, ductility and cost constraints. Understanding post-buckling behavior is vital for assessing structural resilience. Practical example of applications. Columns in buildings, bridges and towers are designed to avoid buckling failure. Reinforced concrete and steel columns are analyzed, considering buckling effects. Advanced computation method assist in predicting buckling in complex structural systems. Summary to key ways. TKways. Buckling is a critical failure mode that can be considered in structural design. Euler's theory provides fundamental insights must be supplemented with real-world factors, proper spent boundary conditions, slenderness, and safety factors ensure sustainability. Thank you, sir.